So the definition is here. It's hypercohomology.
But I had forgotten to press the record button. My apologies.
Yeah, no worries. I was just confused by this voice. No worries. So yeah, so algebraic Derank cohomology was defined by Grothendieck as the hypercohomology of X with coefficients in the complex of sheaves of algebraic differential forms on X. And it's the exact same story as classical Derank cohomology of manifolds, except that here you have a variety that's defined over some field F. And if you're only using algebraic differential forms defined over F, it gives you an F vector space, not only a real or complex vector space. So this is really an F vector space structure on classical Derank cohomology. And Betti cohomology is the dual of Betti homology, which is just singular homology. So this is take the complex points of X. This is a topological space, and take normal singular cohomology of that with rational coefficients. And so on the one hand, you get an F vector space that's finite dimensional. And on the other hand, you get a Q vector space that's also finite dimensional. And it turns out that they have the same dimension. And more importantly, they can be canonically compared after tensoring with C. So if you tensor Derank cohomology with C and Betti cohomology with C, there's a canonical C-linear isomorphism between those two things, which is called the period isomorphism, or the period matrix if you choose bases of both vector spaces. And I've denoted it with an integral sign because that's what it is. You take a differential form on the one hand, you take a topological cycle in Betti homology on the other hand, and you compute an integral. And that's what this is about. Okay, so this is a very basic result that's due to Derank if you ignore the F structure on Derank cohomology, and to Grothendieck if you want to have this F structure, which is very important for number theoretic purposes. Okay, so we're going to look at many period matrices in this talk, and the basic questions, the basic question of this talk is going to be, what does a period matrix look like? That's kind of the question that I want to answer in very specific cases. But before, let's just contemplate some period matrices. So the first one is, if you look at H1 of A1 minus a point, in topology, that's C minus a point, and H1 of C minus a point is one dimensional, so you get a 1-by-1 period matrix. In Derank cohomology, a basis is given by the class of dx over x. And in Betti homology, a basis is given by the class of a cycle, a circle around zero, a loop around zero. And the corresponding integral is 2 pi I. So that's this period matrix. A more interesting one is if you take H1 of the elliptic curve, given, let's say, with an equation of this form, y squared equals x cubed plus ux plus v, where u and v are let's say, rational numbers. Topologically, you get a torus like this. So in Betti homology, you get a basis that consists of the classes of these two loops that I denoted alpha and beta in this picture. So you get a 2-by-2 period matrix, and a classical choice of Derank basis is the class of dx over y and the class of x dx over y. And so you get these four entries of the period matrix, and in the first column, these numbers are typically called the periods of the elliptic curve, because if you quotient C by the lattice that they generate, you find the elliptic curve. Well, you find the complex points of the elliptic curve. And a third example that's going to be much more relevant to this talk is this guy, H1 of A1 minus 0, comma, 1 and A. So this comma here means relative cohomology. It means, topologically, it means that I'm looking at cycles on A1 minus 0 or simplices on A1 minus 0 that may have a boundary along this subvariety here. So from the point of view of integration, it's very natural to want to look at this generalization of cohomology or homology, because when you compute integrals, most of the time, the integration domain is not a cycle, is not closed, it has a boundary. And here you look at cohomology of x relative to y, meaning that you look at cycles on x, which may have a boundary along that subvariety y. All right. And if you compute that specific cohomology, you discover that it's two-dimensional. And let me, well, I mean, in Betti homology, it's kind of obvious because you still have here, this is let me describe your basis of Petit homology. So you have the same closed loop around 0, since it doesn't have a boundary. It's still it still defines an element in relative homology, but now you have your points 1 and A, and you can look at a path from 1 to A that avoids 0, and this is still this is a bona fide element in Betti homology. Okay, so that's the new thing here. And in Derank you have dx over x, and in and you have another element that I'm not going to describe. It's an exercise for you. And if you solve that exercise, you will understand what Derank relative cohomology means. But in any case, if you compute the period matrix, you find this this matrix here, and the important thing to look at is this log A here. So the rest of the period matrix is not very important, but the log A is really the new period that you get by looking at relative cohomology in this sense. Are there questions? No? Is it fine? Okay. And in a moment, I will define or have defined mixtape motives, and mixtape motives are objects that have period matrices, and their period matrices will all be of this shape, meaning they will be upper triangular with powers of 2 pi's on the diagonal. So this will completely rule out period matrices of elliptic curves. Okay, so this is not what I want to talk about. All right. And so I'm going to start with an informal definition of mixtape motives, and to give that informal definition, I need to present a sort of algebraic gadget that's a bit stupid. It's just to make sense of categories of period matrices, and I'm calling this the category, sorry, of period structures, PS of F, for F a number field, let's say, for the rest of this talk. Its objects are just triples consisting of V Derank, which is a finite dimensional F vector space, that you should think of as Derank cohomology of some variety defined over F. V Betti, which is a finite dimensional Q vector space, which you should think of as Betti cohomology, and some comparison isomorphism between the complexifications of those two vector spaces. Okay, and so this is the category. The objects of the category, the morphisms are the obvious ones. And well, to be precise, you need to specify for each embedding of your number field the Betti cohomology vector space and the comparison isomorphism, because for each embedding you have a complex manifold that you can associate to X. Okay, so that's the setting, and you can look at this category, and it's easy to see that everything that you can do with vector spaces you can do with objects of that category. For instance, direct sums, kernels of maps, co-kernels, tensor products, duals, and everything. And in pompous terms, this is called a Tanakin category. So Tanakin category is a category where it's an abelian category, which means you have direct sums, you have kernels and co-kernels, and so on. It's also a tensor category. You have a tensor product, and also you have duals, meaning it's sort of finite dimensionality assumption, and also you have fiber functors. So a fiber functor is a faithful exact functor to vector spaces. So here you can just take an object like this and associate, let's say, Derank, the Derank vector space, and that's a fiber functor, or the Betti vector space. You have two fiber functors that are natural here. Okay, I just wanted to say this word Tanakin because it's going to come up later. An example of an object in this category is what people call the Tate Twist. So the Tate objects that I will be denoting by Q of minus n for the rest of this talk. N is an integer. I should have written this. So n is any integer. And it's just the rank 1 object with period matrix, this thing, 2 pi I to the n in a 1-by-1 matrix. Okay, so before we saw Q of minus 1 coming from the H1 of A1 minus a point, and essentially these guys are tensor products of Q of minus 1 with itself. And these are going to be my building blocks for the rest of this talk. So the informal definition of mixtape motives, so MTF is the category of mixtape motives over F. And the informal definition goes as follows. It's the full subcategory of the naive category of period structures that I just defined, that consists of objects with period matrices of a very specific form. These period matrices should be block upper triangular with diagonal blocks consisting of 2 pi I to the n times the identity. So they have to look exactly like this. And in categorical terms or in algebraic terms, we're looking at iterated extensions of the objects q of minus n that I just defined. Okay, so you have those building blocks q of minus n. You can make direct sum, of course, that's not very interesting. You will have diagonal matrices with 2 pi i's on the diagonal or pairs of 2 pi i's. But I want to look at things which are non-trivial, potentially non-trivial extensions of those objects. And the last bit of the definition, which is in fact where I have to kind of wave my arms, is that these period structures have to come from geometry. So I'm not looking at all possible matrices that would be completely uninteresting. I'm looking at those which come from geometry, meaning that they come in some way from the cohomology of algebraic varieties. Okay. But I want to be more flexible than that because I want a category. So for instance, if you have a morphism between 2 cohomology groups that's natural, meaning for instance that it comes from a map between algebraic varieties, I want the kernel and the co-kernel to also be objects of my category. Okay, so essentially I kind of generate everything with algebrogeometric ingredients. That's what come from geometry means here. Okay. So that's the category that I want to talk about, and the question is, well, what do these matrices look like?
Sorry, Clément, could I just interrupt
Sure.
It's not that you need all the weights there. It's just certain powers of 2 pi I that appear on the diagonal. Is that right?
Yeah, absolutely. Yeah, thank you, Kumar. It's a good point. So these blocks could be empty for certain n's.
Okay. Okay.
Yeah. No, you're right. It was not very clear. Yeah. Absolutely. And in what I'm gonna talk about, I will be interested in examples where many of these blocks are actually empty. That's a good point. Okay. So if you're interested in the formal definition of mixtape motives, it's here in gray. So the formal definition is you have to start with Voevodsky's triangulated category of motives over F with rational coefficients, which usually is denoted by dm over F, dm of F, sorry. It's defined in quite an abstract way where the objects are certain diagrams of varieties, and the morphisms are coming from algebraic cycles. That's kind of the rough idea that you should have in mind. And then you have natural objects that I call q of minus n in there that play the role of our period matrices with 2 pi to the n in them. And you look at the triangulated subcategory that they generate inside this huge triangulated category. And then you define MT of F as the heart of a certain T structure on this triangulated category. So this was done by Levine. And you get an abelian category that's the category of mixtape motives over F. And then you can prove that it's actually a Tanakin category. That's what Mark Levine does in his paper. He proves that you can define tensor products and everything, and that it satisfies the axioms of a triangulated category. So the definition is quite abstract, but you should really think in terms of period matrices, and you should feel free to work with mixtape motives in the same way as you work with finite dimensional vector spaces. You can do everything. And the structure of this category is very easy to explain in some sense. So the simple objects, as I said, are the q of minus n for any integer. And they correspond to those period matrices, which are our building blocks. And then every object of the category is obtained by taking iterated extensions of those things. And more concretely, it has a canonical weight filtration that's denoted W, and which is induced by even integers. It's the weight filtration from mixed Hodge theory, if you're familiar with that. And each graded for the weight filtration is just a direct sum of the simple object q of minus n. All right. So this weight filtration is really the filtration that you see in the block structure of the period matrix. And then you want to understand, well, how can I extend a q of minus n with a q of 0? How can I take two of these building blocks and create a new motive? Well, it turns out that and that's kind of a magical formula that the extension group is computable, at least in the formal definition, because in the informal definition, it doesn't really make sense. But in the formal definition, because the morphisms in Voevodsky's category are related to algebraic cycles, you can compute this X group in terms of algebraic cycles, and it ends up being isomorphic to a K group of F. So this is algebraic K theory of degree 2n-1. So this thing is an abelian group, and you tensor it with Q. So it's a Q vector space. Okay, so if you don't know what K theory is, you don't really need it to understand this talk. It's so K2n-1 of F, at least tensored with Q, is you take group homology of degree 2n-1 of the infinite general linear group of F. So that's the union of all GL R of F with rational coefficients. And this has a Hopf algebra structure, and you take the primitives of this Hopf algebra structure. So it's something that's really related to the general linear group over your field F. And in general, K theory groups are very hard to compute. But here we're extremely lucky that in the case of where F is a number field, this has been computed by Borel. So for n equals 1, it's very concrete. So K1 of any field is the group F star. So that's very easy. So that's F star tensored with Q over Z. That's easy. But for higher n, it's really a deep result by Borel that all these groups are finite dimensional over Q. All these vector spaces are finite dimensional over Q. And the dimension is very easy. So if n is odd, the dimension is the number of real embeddings of your number field. And if n is even, the dimension is the degree of the number field minus the number of real embeddings. So very good. And also another statement that actually comes from Borel's theorem is that the higher x, they vanish. So there's only x1. There's a conductor with and gives back essentially the semi-simplification with respect to the weight filtration. So you take just the direct
I don't know if it's just me or everyone that we've lost the speaker temporarily.
Not just you.
Also, not just you.
Maybe he needed a moment to think.
All right, he's back.
Okay, Clément, we missed you for a little bit.
Oh, you're muted, Clément.
Sorry about that. Yeah, I was disconnected for some reason. Sorry. Let me share my screen again. So when did you guys stop hearing me?
You were just telling us about the fact you get a canonical fiber functor.
Okay, thank you. Right, so there's a canonical fiber functor to Q vector spaces, which is given by this formula. So you take the direct sum over n of essentially this thing is just the weight grade quotient grad 2n of n. And that's a fiber functor. And via this fiber functor, so the Tanakin formalism tells you that n is the category of mixtape motives over F is equivalent to a category of representations of some group scheme. And in this case, the group scheme is essentially a pro-unipotent group scheme. So it's the same thing as a pro-nilpotent Lie algebra. And so you get that the category of mixtape motives over F is isomorphic to the category of graded representations of a certain graded Lie algebra. And because of the vanishing of higher x, that Lie algebra is free. So it's a free Lie algebra. And the generators here are given by essentially K theory here, which are the exponents. So this is a little bit of abstract nonsense about representation theory of Lie algebras and how to compute X groups in categories of representations, but it's very simple. So you get this. So here again, I've been lazy, but this dot here is really the K groups, the extension groups. Okay. So I mean, abstractly, there's nothing to say about that category. It's just the category of graded representations of a 3D algebra. There's nothing much simpler than that. And just to be even more concrete, the category of mixed-state motives over Q is equivalent to the category of graded representations of a 3D algebra, whose generators are given by, well, K theory of Q. So if you look at K1 of Q, there's a basis that's given by someone that I call sigma 1 P for every prime P, because, well, Q star has a basis consisting of, well, log of prime numbers, if you wish. And here for n odd, you get just one new generator, which corresponds to this K group, and I've called them sigma 3, sigma 5, sigma 7, sigma 9, and so on. And they're in degree -3, -5, -7, -9, and so on. And here for Q, all the embeddings are real, so you get nothing here for n even. So that's a very concrete category. And if you want to, for instance, classify the objects in that category, you just have to classify representations of 3D algebra, which is quite easy. But that doesn't tell us anything about periods or geometry or period matrices. We don't see them in this description. It's just useful to know abstractly what's the size of that category. But concretely, if you want to do number theory, it doesn't tell you much. Any questions here? No.
Sorry, I asked a question about 10 minutes ago.
Sure.
You started with DM. You are telling about DM. What DM you mean? Effective DM or DM stabilized in GM direction?
So I guess I really mean, I mean Voevodsky's category of geometric. Well, I mean, yeah, no. So definitely, GM has been inverted in there. If that's your question.
GM is inverted in your DM.
Yeah.
Okay, perfect. Thank you.
Yes. You need to invert GM. I mean, GM is Q of -1, I guess. It's what you mean. Q of -1 needs to be inverted just in order to have duals. So that's the only reason. And if you don't do that, you don't have a Tanakin category, because the Tanakin category.
Yeah, because there are several notations for DM, and yeah, I understand what you mean now.
Yeah, maybe I've been lazy. I haven't put the superscript and subscript, but yeah, that's definitely the one where Q of -1 has been inverted. All right, thank you for your question. Okay, so now I want to spend some time discussing what are the simple extensions of mixed-state motives over F. So right now we have kind of two ways of viewing these things. There's the description that I started with, which is period matrices. So a period matrix of an extension of Q of -1 by Q of 1 has to look like this. So it's a 2x2 matrix where you see the subobject Q of 0. So Q of 0 is just a trivial motive. So it's the identity matrix. And here this 2 pi to the n is the period matrix of Q of -n. And here, since you're looking at an extension, you have potentially a non-zero number rho here in the upper right corner, which kind of measures the extension. Okay, so that's a very concrete thing to look at. And there's also the magical formula from mixed-state motives, which tells you exactly how many extensions like this come from geometry. And the answer is as many as the size of K2n -1 of F. And by the way, this is already super interesting if you're interested in K theory, because this gives you a very concrete way of thinking about K theory. So if you have a class in K theory, you can view it as an extension in mixed-state motives, and then you can look at the corresponding period matrix, and then you can isolate a complex number here that represents your class in K theory. And for people interested in K theory, this rho here is called a regulator. It's a regulator associated to the K class, K theory class. So that's rho is called a higher regulator. And the question is, suppose I take my favorite number field F, I know what the size of this group here. It's just a function of the number of real embeddings of f and the degree of f. So I know how many different regulators I'm expecting. What are these numbers? So that's very basic questions, and these numbers seem to be very important complex numbers from the point of view of number theory. But it's kind of unclear in general how to give an answer to that. And I think that's kind of a crazy state of affairs that we can't answer that question. It seems to be a very deep question. At least for n equals 1, it's easy, and I've already given you the answers. For n equals 1, I've told you that k1 of f is f star. So what is the extension corresponding to a number a in f star? Well, I've described it for you. It's the h1 of a1 minus 0 relative to 1 and a, whose period matrix is this one. So the regulator is log of a in this case. And that's the regulator in the sense of classical algebraic number theory. It's the Dirichlet regulator. So that's why these things are called regulators. All right. For n bigger than 2, again, there's no clean answer to that. A motivation to solve this question, if you don't care about K theory, is that it's important if you want to understand special values of Dedekind zeta functions. So for a number field, you have a basic invariant, which is called the Dedekind zeta function, and you can evaluate it at n, an integer. So it's exactly this sum of series. And Borel's theorem about K theory tells you that essentially, if you take all the possible regulators for your number field, and you take them for all possible embeddings of your number field, you put all of these things in a matrix. Well, the determinant of that matrix is essentially the special value zeta f of n. So if you know an answer to this question of what the regulators are, then you have a formula, a determinant formula for the special value of the zeta function. Okay, it's a determinant of regulators for all the embeddings of the number field. So that's great. And this generalizes the classical class number formula, which tells you that the residue at 1 of the zeta function can be expressed in terms of determinants of logarithms of units. So that's really in this direction that this question is useful for. Okay, so what's the strategy to understand regulators or higher regulators? The strategy is, well, you want to construct as many objects as possible of your category. And you want to use the Tanakin formalism in order to find among your huge family and among the Tanakin subcategory that your object generates, your simple extensions, meaning your 2x2 period matrices like this, or like that. Okay. And the difficulty is that if you define a period, if you define period matrices from geometry, they will almost never be as simple as this. They will be huge, but there's a hope that if you construct many period matrices, then in the Tanakin subcategory that they generate, you will find your gems, which are the extensions. Okay. And the prototype for this strategy is something called Zaggy's conjecture. And I'm just going to explain what this is for n equals 2. So for n equals 2, you look at very beautiful period matrices called dilogarithm motives or dilogarithm period matrices, and they're given by these 3x3 this time period matrices. So here you recognize in this corner you recognize a log period matrix. So these we like. And in some sense, you're looking at an extension of this by q of minus 2 here. Sorry, an extension of q of minus 2 here by a log motive. And here you also have 2 pi times a log, so that's pretty well understood. And this lead to of a is the dilogarithm. So the dilogarithm is the sum of a to the k over k squared. K equals 1 to infinity. That's a very nice classical function. And these period matrices do come from geometry. They're very natural. And since they're small enough, well, it's a good start, okay? but they do not give you extensions because they're too big. They're not 2x2 matrices. But still, I mean, if you've chosen A such that log of A is a rational multiple of 2 pi I, meaning is if A is a root of unity, then here you have something like 2 pi I squared, and by doing a change of basis in your period matrix, you can replace this by 0. And in this case, it means that there's a quotient of your object that's an extension of 2 pi I of q of minus 2 by q of 0. And the period of this extension is Li2 of A. Okay, so that's if A is a root of unity. But in general, it's not as simple. For instance, your number field may not have roots of unity and so on. So you need to be a bit more clever and take many period matrices like this and hope that they generate a subcategory where you can find all of your extensions. And this is a theorem, actually, that was proved by many people. So Bloch, Dupont, Suslin, and Zaggy. So that's kind of between the 60s and the 80s. That tells you that for n equals 2, the higher regulators, meaning the periods of extensions of q of minus 2 by q of 0, are all of this form. So linear combinations of special values of the dilogarithm function evaluated at elements of your field F. And they're not any of these linear combinations. They're very, very special linear combinations. And the condition is exactly this thing. So it's a bit bizarre the first time you see it. So you look at sum of ni, so the coefficients here, times 1 minus ai wedge ai, and you want this to vanish. And this wedge product arises in wedge 2 of the Q vector space F star tensor Q. Okay. And I'm not going to explain how this works, but essentially you see that if you look at this period matrix, the obstruction for having an actual extension of Q of minus 2 by Q of 0 is these two logarithms here, log of A and log of 1 minus A, right? If one of them vanishes, then either a sub-object or a quotient of your dilogarithm motive is an actual extension. But in general, none of them vanish if A is any any element in the number field. They don't vanish, but they're still the two things that control how far you're from having an extension. And your log of A and log of 1 minus A, you find them here. So this AI is log of AI, and this 1 minus AI is log of 1 minus AI. And the condition to have an extension period is exactly this vanishing condition here. Okay, so that's something that was I think found by Spencer Bloch. Okay, right. Do you have questions about this? So that's very nice. That's for n equals 2. So for n equals 2, we have a good control on what the extension periods are, and moreover, we get a sort of recipe for finding them. Good. And the general statement of Zaggy's conjecture is that extension of Q of minus n by Q of 0 in mixtape motives should all live in the Tanakin subcategory generated by the nth polylogarithm motives. So they look like this. So there's an infinite family of polylogarithm motives. I just wrote the n equals 3 case. So here I've copied the same period matrix, and you extend it a little bit with a 2 pi I cube in the diagonal, and here uninteresting logs. And here the famous third polylogarithm. So that's maybe you've guessed, it's sum of a to the k over k cubed. And you have these very nice period matrices, and you have to trust me that they do come from geometry. And Zaggy conjectures. Well, I mean, Zaggy does not conjecture something like that, but that's the reinterpretation of Zaggy's conjecture in those terms. That all the extensions of Q of minus n by Q of 0 can be obtained by combining enough of those polylogarithm motives. And the consequence, which is Zaggy's original conjecture, is that the special value at n of the Dedekind zeta function of any number field can be expressed as a determinant of things involving polylogarithms evaluated at your number field. So that's the concrete consequence of such a question. And what is known about this is not much, For all n, if f is a cyclotomic field, the conjecture is known. But again, it's because if you take a root of unity here, you have all of this complicated period matrix that is filled by zeros, essentially, because you can just do a change of basis to replace those logs by 0. So it's very easy for cyclotomic fields, and it's known for all number fields if n equals 2. That's the theorem from the previous slide, but also n equals 3, which is a theorem by Goncharov, and for n equals 4, which is a very recent theorem, maybe 2 years ago, by Goncharov and Rudenko. So there's progress on this front. So that's a prototype of questions where you might understand in some sense what the extensions are and what the period of the extensions are. But at the end of the day, it's not extremely explicit, because you have if f is a number field that's not Q or a cyclotomic field, then you really do have sometimes very weird looking linear combinations of lead twos, for instance. So it's at the same time satisfying and a little bit awkward from the point of view of number theory. Okay, so that's one of the things that I wanted to explain related to extensions and mixed state motives. And another thing is some more concrete questions that are motivated by diaphantatic approximation, and more concretely irrationality proofs for certain mathematical constants. So here's an intermission in this talk: how to prove that some real number alpha is irrational. So you have your favorite constant alpha and you want to prove that it's irrational. Essentially, all irrationality proofs go along the following lines. So you find integer sequences ak and bk, such that the linear combination ak plus bk alpha is always positive and goes to 0 when k goes to infinity. If you have that, then you have a proof that alpha is irrational, because if alpha was rational, then by clearing denominators, you would be faced with an integer sequence which is made of positive integers, but which goes to 0 when k goes to infinity. And of course, that's not possible. Okay, so essentially, all irrationality proofs in some way work like this, more or less explicit. But I'm interested in explicit irrationality proofs, where the sequences ak and bk are somewhat explicit. And I'm interested in cases where these things come from integrals. And in many cases, that's how they arise. And there are integrals of the form integral in some domain sigma that is fixed of f to the k times omega. So f is a function on your domain. Omega is a fixed differential form, and you're just raising f to the power k and letting k go to infinity. And hope that this integral evaluates to a linear combination of 1 and alpha here, uk plus vk alpha, as in the criterion. So two remarks. So first remark, it's easy to produce integrals like that are very small. That's the main point of looking at integrals, because if f is very small on sigma, then your integral will go exponentially quickly to 0. So that's the main advantage of working with integrals. You can very easily compute and produce integrals that are very small. The price to pay, of course, is that by computing integrals, you have to compute antiderivatives, and you create denominators. So there's no way that these coefficients will be integers. They will be rational numbers. And when k go to infinity, the typical behavior is that the denominators of uk and vk will go exponentially quickly to infinity. So if you want to apply this criterion, you have to multiply by the lowest common denominator of uk and vk and hope that the criterion still applies, meaning that when you multiply this integral by this denominator, it still goes to 0 when k goes to infinity. So you have this game, this Diophantine game that needs to be played. You need integrals that are that go exponentially quickly to 0, but they have to go to 0 quicker than the growth of the denominators of the coefficients here. Okay, so that's the strategy. And in many cases, well, in some cases, it works, and it's the it's the simplest irrationality proofs for certain constants. So the simplest example is log 2. So if alpha is log 2, I'm claiming that the simplest irrationality proof for log 2 is as follows. So you look at these integrals. So here my domain is 0, 1. My differential form is dx over 1 plus x. So if k equals 0, that integral is really log 2. but then you insert a function x1 minus x over 1 plus x to the k, and because this bracket is very small on 0, 1, it's clear that this integral is converging exponentially quickly to 0. It's always positive, of course, and it's a very simple exercise to show that any integral like this will evaluate to linear combination with rational coefficients of 1 and log 2. But of course, UK, because you've computed antiderivatives, it's going to be a rational number, so it's going to have denominators, and you have to compute those. But you have to trust me that, and it's a very easy exercise that you might enjoy doing. If you estimate the denominators of UK, you realize that you do have a proof that log 2 is irrational. Okay, and the main point of this last part of my talk is that this strategy really applies to higher regulators. This strategy is made for higher regulators. In other sense, higher regulators, meaning periods of simple extensions, are a class of mathematical constants for which there's a hope to be an irrationality proof like this. And morally speaking, they're the only numbers for which you can hope to have simple irrationality proofs like this. So what's the connection? Well, it's simple. Suppose that you have a motive, which is your favorite simple extension. So it has this form. So that's an extension of q of minus n by q of 0. You have your regulator here, which is the constant alpha that you're interested in, which is called rho. What does it mean to have a motive? Well, it means that it comes from some cohomology group. So here you have a basis of Betti homology, and here a basis of Derank homology. And the first row of your matrix is indexed by some element in Betti homology, which, if you're coming from geometry, means it's some cycle sigma, potentially with boundaries. Okay. And I'm claiming that such a matrix, such a period matrix, is a machine that produces linear forms. And why is that? Because now you can choose any differential form giving rise to a Derank cohomology class, and you can pair this differential form omega with this fixed cycle sigma. And this integral will always be, no matter what omega is, it will always be a linear combination of the two entries of the period matrix, which are 1 and rho. So you get a rational linear combination of 1 and rho. And that's what you need in order to have an irrationality proof. Okay, I hope that's clear. So here I'm cheating a little bit for many reasons. One reason is that a priori you would have F coefficients, but in many situations you have a rational structure that helps you have rational coefficients. That's the first thing that I want to say. And the second thing is that, well, I mean, there's even if you get such a construction, you need to then evaluate and estimate the coefficients, and this might not lead to an irrationality proof. You have to be extra lucky after this first step. But I guess the point I want to make is that you don't need to know that these extensions exist, and you don't need to know what rho is. You also need to have a geometric way of understanding these extensions. You need to construct these extensions geometrically, meaning coming from actual cohomology groups, because you need to have actual integrals here to compute. Okay, so that's kind of the next step. When after understanding what the extensions are and what the regulators are, the claim is that if you manage to construct these extensions geometrically, you have a machine that produces linear forms and maybe irrationality proofs. And you see that it's not enough to know that your period matrix lives inside some bigger period matrix, because you will get parasites coming from other periods that you don't care about, that do not contribute to the extension. So why is this not a crazy dream? Well, let me specify to f equals q now. So f equals q, I already said that there are very few extensions. So the extension of q of minus n by q of 0, they're all trivial if n is even. And if n is odd, there's essentially only one extension. And the periods are zeta of n. So these are the regulators in this case. So the odd zeta values are the regulators for the number field f equals q. And by the way, these are the values of the polylogarithm function at 1. So this is very much in line with Zaggy's conjecture. And Brown has constructed, Francis Brown has constructed the first non-trivial extension, which is E3, where zeta 3 appears in the period matrix, completely geometrically, as a relative cohomology group of some open in the moduli space M bar 06, relative to some divisor. So M bar 06, you don't really need to know what that is. I just wrote this like this in case some people recognize it, but it's a very explicit rational variety, smooth projective variety, which is an iterated blow up of P3. So you can kind of imagine that this is essentially P3. But M bar 06 comes with a very nice combinatorial structure with a normal crossing divisor at infinity indexed by partitions and everything. So A is some very nicely chosen union of irreducible components of that divisor, and B is another one like that. Okay, and Brown picks A and B in a very clever way, so that this motive, this mixtape motive, has a period matrix which is this thing with n equals 3. And so this gives a machine for producing linear forms in 1 and zeta 3. And if you run the machine naturally, it spits out a family of integrals that were known before to the people who proved that zeta 3 is irrational. So Apéry proved that zeta 3 is irrational by using some very clever things. And this was essentially at the same time reinterpreted by Fritz Böckers as coming from integrals. So these are the integrals that Böckers writes to explain the proof by Apéry. And these are the integrals that come out naturally of the machine that Brown produces. So really this strategy in the first case, it really gives the natural or the well-known irrationality proof for zeta 3. So it gives us hope that maybe we can go further. At present, no geometric construction of these extensions are known except for this one. So for n equals 5, we don't know how to construct E5 geometrically. I would love to understand that. And it has to do with the fact that we don't know how to prove that zeta 5 is irrational. And we don't know how to prove that any odd zeta value is irrational apart from zeta 3. So it's kind of the same. I mean, it's two questions that sound very different, but they're in the same, I mean, they're the same type of difficulties that from the mixtape point of view, you can produce many motives with zeta 5 in their period matrices, but they're going to be too big. And so on the first row, you're going to have 1 zeta 5, but also things like zeta 3 or zeta 4 in the middle. And this will be a machine to produce linear forms that will have 1 zeta 5, but also parasites in the middle that you don't care about, like zeta 3. And that's a phenomenon that people who've tried to prove that zeta 5 is irrational know very well, because if they try to adapt the Apéry or the Böckers strategy, they find linear forms with 1 zeta 5 and other parasites in the middle. So it's really two different ways of approaching the same difficulties. But yeah, the point of view of algebraic geometry maybe help clarifies this and maybe helps telling you where to look for these extensions. Something that is doable, and that's something that I did 5 or 6 years ago, is to construct some of the next best thing, which is a motive that is the minimal one with all the non-trivial extensions in there. So you have the extensions E3, E5, E7, and so on. And what I could construct geometrically is what I pompously denoted by the co-limit of these extensions, which is just this period matrix here. So it's an infinite period matrix, but of course you can truncate it anywhere you want. And you have all the extensions at once in this period matrix, and they all appear once, and there's nothing else. There's no parasites like even zeta values and so on. And here the difficulty is to get rid of the even zeta values. So the even zeta values are related to powers of pi by Euler. So because pi is transcendental, if you have even zeta values in your linear form, you're going to prove a theorem from the point of view of Dirichlet approximation that's way less interesting than what people knew in the 19th century about pi. So you have to get rid of even zeta values if you want to prove something interesting. And this geometric construction that I may or may not have the time to explain actually recovers some Diophantine approximation result by Boll and Rivoal in 2000 or 2001. Boll and Rivoal, so if you use the construction that I gave and as a machine to create linear forms in 1, zeta 3, zeta 5, zeta 7, and so on, you naturally recover a family of integrals that Boll and Rivoal looked at around 2000. There are certain integrals of this shape here for certain well-chosen parameters ui, vi, and n that evaluate to linear forms in 1, zeta 3, zeta 5, and so on. And Boll and Rivoal used them to prove that 1, zeta 3, zeta 5, zeta 7, and so on span a Q vector space of infinite dimension, which allowed them to prove that infinitely many odd zeta values are irrational. And the difficulty in their proof is exactly the same as the difficulty in my geometric construction, is to get rid of the even zetas. And maybe I can say a few words about some work in progress in this direction. So that's in progress with Daniel Juteau, who's in Amiens in France. So first of all, we're doing experimentations with motives that are of the same shape as the Apéry motive that Brown produced. So Hn of m bar 0 n plus 3 minus some stuff relative to some other stuff. So these are motives that are mixtape motives over Q and even over Z. They're unramified at every prime number. So they're exactly in the right family of motives. And there's a chance that if you choose A and B carefully, you might find interesting extensions, but it might be a bit too naive. And you need to add a little bit more to the mix, and what you add is symmetries. So these things come equipped with actions of finite groups. So the point of n bar 0 n plus 3 is that it carries an action of the symmetric group Sn plus 3. And if A and B are symmetric enough, you might have a big enough finite subgroup of Sn plus 3 acting on your motive, and you might be able to use it in order to reduce the size of the motive and find your hidden two-dimensional extension inside. So that's one thing that we're experimenting, and these things are very, very hard to compute. So we're giving these things to computers, and the computers are doing the heavy lifting for us, and they're spitting out the shape of the period matrix. And so the difficult part of it is how to explore this massive haystack, which is the space of possibilities, to find our needle. And right now we're making progress, but we're still not at the end of this road. And another thing that you can do is working just in n equals 2, so meaning two-dimensional varieties, and experiment in the same way with reflection arrangements in P2. So reflection arrangements are arrangements of lines in projective space, projective plane here, which have very interesting symmetries. And the symmetry groups are called reflection groups. Complex reflection groups, and they're typically defined over some quadratic extension of F in many cases, in many interesting cases. So you can look at the list of reflection arrangements and try to use this kind of geometry to produce interesting motives, and then use symmetries that are present in this case to reduce the size of the motives and maybe find extensions. So that's kind of what we're doing at the moment, and maybe I can stop here if you have more questions about my work or other things. I can tell you about it, but I guess that's all I wanted to say. So thanks.
Okay.
Very nice talk. Very nice talk. Any questions?
Yeah.
Yes, please.
Yeah, I have a question. Firstly, yes, it is a very, very beautiful talk. I really like the construction. So I may ask about this attempt to find these motives. So you're taking some high projector space and doing some blowing ups, and so is the problem combinatorial, really, in understanding these arrangements?
Yes. Absolutely. So you can view things inside projective space. So let's talk about projective space. So inside projective space, you have hyperplanes Zi equals Zj, Zi equals 0, and that's it. And that's your game. And you want to use these things to define cohomology groups. But of course, you kind of need to blow up to define the cohomology groups, but the combinatorics is already present in projective space. So indeed, there's a finite number of things that you can do because you have a finite number of hyperplanes. So there's only a finite number of motives that are going to arise from that geometry. But that number is huge as soon as n is bigger than 2. And you don't want to test them all. That's one thing. And then you want to be able to compute them, at least the semi-simplification of those motives. And that's also in principle a combinatorial thing. And in previous work during my PhD thesis, I developed an algorithm, a combinatorial algorithm to compute those motives, and we have implemented it with Daniel Dupont, so that the computer can really say, well, this motive has semi-simplification Q of 0 plus Q of -2 plus Q of -5 and things like that. So this is exactly what we need in order to check if we're close to finding an extension. One problem that we have is that there are many things to check, and we need to be able to tell the computer where to look for, because the haystack is really huge. And the second thing is that the cohomology groups, which in practice are very small, like the total dimension of the period matrices is usually something like less than 6, but the algorithm goes through massive homological algebra computations, and it's very, very long as soon as n equals 4 or 5. So we also have limitations in terms of computation time. But yeah, in practice, it's a combinatorial thing. But also you have to add other things to the mix, right? You have to use the symmetries. So that's another thing that's also purely combinatorial, but that kind of adds to the complexity. And you also want to use natural morphisms between all these groups. So the naive thing is that one of these groups is an extension that we're looking for. But that's probably not the case. It's probably too naive. So you have to use many other things. So for instance, in the Ball-Riemann story, there's a symmetry, there's an S2 symmetry, a Z mod 2 symmetry, there's an involution that plays a very crucial role in order to get rid of the even zetas. And you can phrase it in terms of some Z mod 2 inside some symmetric group S8, sorry, not S8, well, SN in general, acting on a certain motive. So that's very useful. So you need to be able to put all of this into the mix, and yeah, in principle it's combinatorial, but you need to be a bit clever. So that's what we're trying to do with Daniel at the moment.
And the other thing is also something you alluded to right at the very end, namely, you can still look at a zeta value like zeta 3, but now change the field. So what if you look at, I don't think we know the analog of FFE for a number field, do we? Zeta FF3?
Yeah, so that's kind of the idea of this kind of second project here.
Yeah.
But already for n equals 2, it's interesting. So for n equals 2, as I said, if you take a number field that's totally real, it's completely uninteresting. But if you take let's say an imaginary quadratic field, you already have an interesting period that is kind of a cousin of zeta 2. And maybe one of the first cases that you want to look at is f equals q of I. So Gaussian numbers. In this case, there's one interesting period matrix like this. That's non-trivial. And here you essentially have something. You have G here. So G is Catalan's constant. It's a very well-known mathematical constant. It's I might mess up here. Sum n equals 1 to infinity minus 1 to the n over 2n plus 1 squared, I think. So it's also a special value of an L function associated to a Dirichlet character. So yeah, so already for this, by looking at interesting geometries defined with this field, you might have a chance of proving that this number is irrational. And it's an open question. Like, people would be very interested in having a proof that this number is irrational. It's the kind of mathematical constant that people like in Diophantine approximation, because it comes up all the time because it's so simple from the point of view of arithmetic geometry. So that would be the second wild dream, would be to prove that this number is irrational. But already having a construction of the extension is non-trivial. I don't really know how to do it geometrically.
Thank you.
Any other questions, anyone? I thought I saw a hand raising at some point, but I don't remember who it was. If anyone, if there are no questions right now, then I'll ask a question, Clément, if you don't mind. Could you go back to that slide where you talked about the Zaggier's conjecture? First, maybe the 3 by 3 matrix.
Oh, yeah, the dialogism here. Yeah.
The dialogism, yeah. Right. So here, okay. So you said that there's actually a geometric construction for this motive. Yeah.
Yes.
Okay. And then, so here's my question. So, okay. So the weights of this motive are what? Are 0, 2, and 4, right?
Yes, 0, 2, and 4 here. Yeah.
Okay. So if like, I think maybe in an email, I wrote to you briefly about this. So let's say we want like 0, 2, and 6. And then like, is there anything known about that, or?
So if you want 0, 2, and 6, so replacing
or
this
0, 2, and 8. Yeah, exactly. Yeah.
Sure. You replace this 2 by 3 or 4 or whatever.
Yeah, exactly. Yeah.
So I mean, the abstract structure of the category tells you exactly how many such objects there are.
No, sure, but if you wanted to have like the actual period matrix.
Yeah, but for the actual period matrix, it's difficult to priori. I mean, there's no answer, there's no clean answer to that. I mean, first of all, you need to specify the entries that are not kind of on the top right corner, in some sense.
True. Yeah.
And even if you know them, there's no recipe for guessing what the remaining period is.
Yeah. So I was wondering if this like geometric construction. I'll ask you maybe for a reference for this, because I think we should look at with Kumar. We should look at this geometric construction and see if you replace the weight 4 with a higher weight, if there's a way that this geometric construction is still.
Yeah. So just for me to understand, this motive is geometrically constructed.
So there are two answers to this. So first answer is that this is a sub-motive of a very big thing, which is the motivic fundamental group of P1 minus 0, 1 infinity with base points at 1 and A. But this is a huge motive, but it's inside there. But in order to cut exactly this very nice matrix or this very nice matrix here, it's not enough. And a work in progress that I hope will soon appear with my colleague Javier Fresal, which will speak at this seminar in a few weeks, if I understand correctly, is giving a very concrete geometric construction of those polynomial motives. I think up to now we didn't have a really geometric construction. And by geometric, I mean that does not use the Tanakin formalism in any way. So nothing abstract, just a relative cohomology group, and that's the one. So we do have that, yeah. But I mean, if you replace 2 by here, you're 2 by 3 or 4. I'm guessing that you will have the same kind of Diophantine problem that I have, because as soon as you have big gaps between the weights, you're kind of faced with parasites in between, or Diophantine parasites, because you want extensions that are far apart. So I'm guessing that's a difficult problem. But if you just want to guess the period, you need something a bit less ambitious than that. You simply need to know that such a motive is inside a bigger one that you can construct geometrically. And these are kind of two different questions.
Oh, I see.
The actual geometric construction is really suited for Diophantine approximation applications. But if you just want to know what the periods are, you need less. I mean, it's a less ambitious goal. I mean, it's a bit different because in the Diophantine approximation, I know what the period is, and I want to prove that it's irrational. But here, you want to guess, you want to know what the period is. So it's a bit of a different question, but I guess the strategy is like for Zaggy's conjecture, right? You have to produce many motives, and then use this kind of. So this is what people call the motivic Lie co-bracket, which is some version of the Tanakin formalism. It's a shadow of the action of the Galois group on the motives. And that's the thing that controls the structure of the motives, and that's the thing that tells you when inside your motive you have such and such smaller structure. So there might be something to look in this direction. So use this extra Tanakian formalism in the shape of motivic coaction or motivic co-bracket or whatever people call that. That might be an interesting thing to look at.
And then the general Zaggy conjecture that I guess you have on the next slide. So this is probably a naive question, but let's take this for granted. This, of course, still doesn't imply that all the periods of mixed state motives over F are algebraic expressions in multiple polylogs. It doesn't imply that, right?
Not at all. So that's a good question. So this type of conjecture only tells us something about simple extensions. It doesn't tell us anything about the whole category. And in general, there's another related conjecture by Goncharov that tells us that the periods of mixed state motives over a number field can all be expressed in terms of multiple polylogs, not just simple polylogs like this, but multiple polylogs. But that's kind of a different conjecture. This conjecture of Zaggy is only about classical polylogs and simple extensions. And it doesn't tell us about the structure of the rest of the category. Yeah, not at all.
Any other questions? I don't see any questions in the chat box. No one has their hand up. Okay, so in that case, we'll thank Clément again for a beautiful talk.
Thank you. It was a pleasure.
It was very nice, very nice. Let me stop the recording here.